Hello and good morning, everyone. I'm pleased you're able to join us for today's Ask the Experts presentation sponsored by Qualmark. I'm Cami Marsh, Qualmark's Global Marketing Manager, and I'll be your moderator today. Today's Ask the Experts broadcast is being recorded, and a link will be emailed to you should you wish to replay any portion of the presentation. Go back and review it and share it. We highly encourage that. And also, questions can be submitted at any time during the broadcast by text using the chat screen. We'll answer as many questions as time allows at the conclusion of the presentation. And we're most pleased to be delivering to you today some timely and deeply valuable information. And so with that, Qualmark Center of Excellence is hosting today's presentation titled Integrating HALT into the Product Development Process with our guest speaker, Mr. Adam Barrett from Apex Ridge Reliability. Adam is a reliability engineer with extensive experience in program strategy, accelerated testing methods, HALT, HAS, QALT, ALT. In the course of his work, he has advanced products in the field of robotics, medical device, consumer electronics, and heavy equipment. And so at this time, I'd like to introduce Mr. Adam Barrett to get the presentation started.
Thank you, Cami. It's really exciting to do another one of these webinars with Qualmark. Apex Ridge Reliability is a company that I started, and what we look to do is help companies in all different fields and disciplines advance the reliability of their products by providing them a very broad set of services, everything from education to testing, design, and execution, to facilitating programs like reliability growth and FMEA. And I welcome you to come take a look at our website, apexridge.com, at some point, and also check out our blog. So today we're going to be talking about integrating HALT into the product development process. And this is something that I'm very excited about because I think a lot of times people experience HALT and they experience it as a very small part of their process, and they simply see it as a test that is done. But if we really fully look at the full scope of what HALT can do in integrating into the process, we can see how powerful it really can be. So I'm going to start off with a little description of HALT, and just to kind of help people who aren't familiar with it get to understand it a little better. And then we will start to go into how you can take this tool and expand its usage. And you will be able to also define metrics and be able to use those to track the progress. So the definition of HALT is that it's a highly accelerated life test. It's actually been redefined as highly accelerated limit test. And the idea is to ruggedize the product and obtain large margins over the expected in-use conditions. It uses all stresses which can cause failures, and stresses are not limited to field levels or stresses. And that last sentence is very important, because that's one of the biggest hurdles in getting people to accept HALT, is there is a natural resistance to putting stresses on the system that far exceed the field stresses. And this idea of wanting to pass the test it's a dramatic shift with HALT, because the idea is you want to fail the product in the test because you want to observe the failure modes, which means you're going to continually increment the stresses until you get failure responses so you can do root cause analysis. So HALT helps the development process by quickly discovering failure modes. It evaluates design margins. It helps support the release of a mature product because you've had an opportunity to see a wide set of failure modes, and they've probably driven some corrective action and design changes. And if done early enough, are effectively free changes. This can dramatically reduce development time. And again, you don't want to pass or fail it. It's a discovery tool. We really should talk about it as a discovery tool. That's the correct frame and not just simply a test. So let's take a quick look at the process itself. There's 4 clear sections of the process. You're going to stress the product. You're going to do this in incremental steps. You want to start off with lower stresses and be getting good response and functionality of the product, and continue to increment it because you want to see how its performance changes as you're incrementing the stresses. Next, you want to make sure you're able to observe failure modes and performance variability. So you want to have the correct metrology on the product. You don't just want to be measuring the stresses you're putting in with accelerometers and temperature sensors. You want to make sure you're monitoring the product performance correctly. So what are the important functionalities that you should be monitoring? This is important to have thought about in advance, and this will help you with the next step, which is to analyze. Effectively, what's occurred in the HALT test, you can consider it a crime scene. Something's happened, and we need to start the detective process of understanding it. And this is one of the reasons whenever you develop a HALT test, I push very hard to have the design engineers attend the test, because with some other tests, the engineers might feel like being present isn't important. And that is because they set up specific conditions and they're interested in if the unit has passed or failed it. But that's not the value of HALT. The value of HALT is causing the failure and getting a chance to observe it. And for that to really be done effectively, the engineer should be there and be participating in the root cause analysis. This also may yield some improvements that are done right there on site, where you can actually continue it and see if an improvement or an isolation of a stress, you can see the product perform better. And this, of course, will lead to ultimately design changes to fully improve the product, to see if you can not only temporarily improve its performance in relation to the stress, but can you create design changes that permanently assist. So once we really fully frame it as a discovery process, we begin to see its full potential as a development tool. And what we'll quickly see after that is how it can be used in conjunction with other common product development processes and tools, and that it will yield benefit beyond what an individual HALT test can contribute and what an individual tool like an FMEA or FDA can contribute on its own. When used in conjunction, they actually will contribute something quite unique. So let's talk about reliability integration, because that's what we're talking about. We're talking about looking at the bigger picture. The bigger picture being the whole product development process. So again, like I said, my focus here is to take HALT away from being just one step in the process. And if you lay it over the whole process, where are all the opportunities to use it? So reliability integration is this taking time in designing your program to look at these opportunities. So let's look at what might be a typical product development process. Typically, it might be broken down into 4 main sections: concept phase, the design phase, a prototyping phase, and a manufacturing phase, or transferring into manufacturing. And there's a lot of tools that can be used. And these tools typically are put into the brackets where they're believed to be able to be executed as early as possible. And you always want to do them as early as possible because they're most likely going to have a bigger impact with the results they generate. For every phase later that you use the tool, you will yield the same valuable input from the tool, but it's harder to implement and have it drive design change if the process is that much more matured. So these are some spots where HALT testing can be inserted. And you can see it's in here multiple times. In the design phase, there might be an opportunity to do HALT testing on a subassembly, so a small component. Typically, you will have people believe that they have to have a complete system to do HALT testing. But there might be areas of the design, especially critical technology changes that are done in subassemblies where you really want to understand it. You want to understand these failure modes because you don't have legacy information on it. Next, there might be another opportunity at the next level up to do it at a higher level assembly. And then, of course, once you have the full system, you want to do HALT testing there as well. So with HALT in the process in multiple locations, what are some ways it can interact with other parts? Well, here's some other tools that I've seen great benefit in interacting with HALT. You can see a DFMEA is highlighted, design failure modes effects analysis. This is a process that a team does to hypothetically look at failure modes. We'll talk more about that. There's fault tree analysis, and you have component selection. Your suppliers are an extension of your engineering team. And the practices that your team does with HALT should be pushed down to the suppliers. They should be doing the same practices because with a lot of modern day development programs, the suppliers actually contribute a significant amount of new technology. Later in the design phase, you can see that there's possibility for interaction with stress strength analysis and design of experiments, and I'll talk about that more as well. And once you are at the prototype phase and you have a full system, you can begin to use HALT to work with trying to make statements such as when is wear out using accelerated life testing, and also improving your root cause analysis method, because you've not inadvertently created some techniques for root cause analysis with the engineer, as I encouraged, being on site, trying to understand what's happened when the HALT failure modes have occurred. So here is a very important point in this process. Taking the time to identify what are we trying to improve and what are the metrics for design improvement. Without defining these, you can quickly end up going down a path that's not going to yield beneficial information. If we haven't identified what exactly we're trying to improve, and we haven't identified how we're going to measure it, how do we know we're progressing in the correct direction? Or if we've actually created good results, how do we really assess the value of what we've created? How do you communicate to the rest of the organization that this is valuable? Without a metric that can be communicated, and also the metric can be multiple metrics. You might have a metric that's reliability. You could have a metric that shows warranty costs likely saved, or it could show dollars in profit or market share growth. And all these metrics can be attached to the HALT process. So this is very important, and I'm going to focus a lot on this metric. So where do we start? How do we create a metric? What do we frame it with? Well, one common way that I like to frame it is within the foundation of the bathtub curve. And for those that aren't familiar with the bathtub curve, the bathtub curve is created to demonstrate what is a very common progression of field reliability with a group of products. So if you are to release a group of products, this bathtub curve is a representation of what the failure rate will be like for the population. So you'll see there's three main sections here. There's infant mortality, useful life, and wear out. So infant mortality is the period which has a failure rate that's driven very much by quality, failures, and defects. So effectively, this is those first few months for a lot of products where quality defects are affecting field failure rate. After this infant mortality period, and the quality failures have been effectively scrubbed out of the population by being removed through warranty removal or replacement or repair, you have the useful life period. And this is the period of time that the customer expects to be able to use the product. And a lot of times for the population that's out there, this will be represented by a constant failure rate. And the reason why constant failure rate is used is because with complex products, complex electromechanical products, or even just mechanical or just electrical, there are so many different failure rate distributions for the individual components that acting all together can be pretty easily measured with a constant failure rate. So even though at different periods of time in the useful life, you might have specific failure modes that are more dominant than others, overall, it's quite acceptable to initially characterize it this way. So these failures will be driven by stress-related failures, which are common usage stresses. At some point later on, the failures will begin to increase, and this will be driven by wear-out failures. So this is when predictable components will predictably begin to wear out, and you'll see an ever-increasing failure rate that will usually ultimately yield with the entire population failing due to dominant wear-out failure modes. Now, there's, of course, a lot of common methods for extending this. One is to suggest that the product be removed and replaced before this occurs. If you've done the testing to understand when this will occur, and you can tell the customer. There are preventive maintenances, which can be scheduled, which take failure modes that would be the primary driving wear-out failure modes and effectively resets them by removing that component or refurbishing it. And with these techniques, you can effectively extend the useful life infinitely for the application. So infant mortality, let's take that as our first metric. And then we'll take a look at how HALT testing can improve this and how we can use it as a metric. So infant mortality is a metric. The way to improve it is you want to shorten it. You want that infant mortality curve to be very steep and very short. And what that means is any quality defects that occur show up immediately. And if you have methods for exposing them immediately, you can effectively keep them entirely in-house in your manufacturing inspection process. So how can HALT help with this? Well, the way it can assist most directly is with HAS and HACCP testing. HAS testing is a highly accelerated stress screen, and it's a screen that's created as a derivative of the HALT investigation. When HALT's done on the full system, there will be relationships established between the stresses and failure modes. You can use this information to create stress profiles that don't break the product, but very quickly remove what are known as common quality defects. So this is very powerful and typically will replace other manufacturing test practices like burn-in and environmental stress screens. Once this system is very well established and in control, you can actually change it to an audit. The HAS stress screen is done on all products, all manufactured components and products. HAS says when you change it to an audit where you take a statistically significant part of the population and you do these methods. And you constantly do it as a closed loop system. And what that closed loop system will do is allow you to update your HAS and HACCP profiles as well as get an understanding of how your manufacturing is changing. So this will decrease field service and warranty costs. It'll reduce the infant mortality rate, and it will help you find issues you would not have found in burn-in. So all of this will reduce that infant mortality period. And there's no way to develop a HAS profile if you haven't first done HALT testing because it is established in what's learned in HALT. HAS profile may look something like this, where if you have a chart of the stresses and then performance of failures, you have your product specifications. Those product specifications are what the customers recommended, how they're recommended to use it. You have your lower and upper operating limits, and this is the point at which the product is from testing the streams that it can handle and still provides response. And then you have the destruct limits. Well, as you can see here, the HAS test range that was created is very broad. Now, this, of course, if not done correctly, can be very detrimental to your yield because you might be destroying product that is good product. Because that is typically the very conservative side of with environmental stress screens, as you see there in the red in burn-in. They tend to only find a very small percentage of quality defects. And those quality defects are in no way what reflects what will occur in the bigger population, which is why there's warranty expense and customer dissatisfaction. So this HAS test range, because of what's been learned in HALT, can fully capture a much larger part of quality defects and keep them in-house. The next metric is, let's take the useful life metric. And this is the performance and failure rate during useful life. And of course, the intention here is to lower this as much as possible. We would like to see the failure rate during useful life be lower. And this is probably the most significant reliability metric because this is what's advertised with a product. When you advertise the reliability of a product, we have a product that's 99.99% reliable. We're talking about the reliability, this failure rate during useful life. So what are some tools that can be used in conjunction with HALT that will improve this? FMEAs are one, as you saw I showed before in the chart. FMEAs will identify the areas of highest system criticality for testing focus. So if we expand that to where we directly look for opportunities in HALT for these areas in FMEA that are considered to be the biggest threat to the product's success, it can be very powerful. And it can also identify non-relevant failure modes, areas we don't want to waste time doing testing. Fault tree analysis. We can identify failure modes for a fault tree analysis investigation. Fault tree analysis are very focused, looking at understanding all the factors that go into a failure mode. Well, within HALT, we've observed some relationships between stress and failure. That can greatly assist in making a much better FTA. Design of experiments. Design of experiments, there's a lot of challenges with correctly setting this up and selecting the right variables and factors. And with what's been learned in HALT, you can do this much more successfully. And the stress strength analysis. We've begun to establish relationships between stresses and failure modes. And so then doing that before you do a stress strength analysis can greatly advance it before it's even been started. So let's take a little bit of a closer look. So a failure modes and effects analysis is a methodology for understanding failure modes and identifying their impact on the system. You have your severity. You give a score to severity, which is going to be based on a scale 1 to 5 or 1 to 10, which is identifying the amount of impact the failure mode has, that the hypothetical failure mode that's been identified has on the product. The likelihood of occurrence. This is an indication of how likely this is expected to occur in normal usage in the field. And you have the detectability. Can this failure mode be detected in advance, not after, in advance of it occurring so it can be mitigated? And all three of these are ultimately going to drive the RPN number. And this is the risk number for that line item. And it's simply the product of those three numbers. So how can this link with HALT? So let's take a look at going from the FMEA being done in advance to HALT. If you had a line item, and in this case you can see the remark was based on this very high RPN number and a concern with binding, we wanted to build a bench setup for measuring the performance of the sensor under these stresses. Well, instead of just the bench setup, how about if we've identified this as such a severe and significant threat to the performance of the product, why don't we also do a HALT test focusing very much on putting that stress in there and monitoring the binding? So in this example here I have, what we did is we put accelerometers right at the pressure sensor and valve. And we wanted to measure the response there, and that helped give us an indication of binding, even if we didn't directly measure binding during the test. So we were able to identify the stresses that were at risk of causing this binding far beyond what was able to be done on the bench test. So with the FMEA being done in advance of the HALT and the results taken right to the HALT step, we were able to improve the HALT by having focused on the right parts of the test. And this may have been something that may have been discovered in HALT later, but you probably would have had to do a second iteration of it when you found out this was of concern and you wanted to measure more clearly. But here we set up the metrology correctly the first time. So what about if HALT is done first, the HALTs that are done before DFMEA? Well, in this case, we discovered that a PCB connection easily disconnected under these extreme stresses. Well, we looked back at the DFMEA and we realized that we didn't put a high likelihood of occurrence for this happening. And it actually ended up having a very low RPN number. But with the HALT testing, we found out it actually was a much higher sensitivity than some of the other line items that had higher RPN numbers. So went back, changed the occurrence, which ultimately changed the RPN number, and saw it rise to the top. So what it did is it took this issue that in the FMEA we didn't, in speculation, think was going to be critical. We were able to put in there the reflection of, in testing, it actually was very sensitive. And this helped update the FMEA to be a better document and drive better design decisions as the team uses it in FMEA in continuing the design process. What about design of experiments? Well, design of experiments, it's a method to determine the relationship between factors affecting a process and the output of that process. We're looking for cause and effect relationships here. And also with design of experiments, a very powerful part of it is interactions. What are the interactions between different variables at set levels, where those variables adjusted on their own don't have the same effect, but together in conjunction do have an effect, and we want to find that. And trying to do this can yield to very large experiments where a lot of times DOEs are trimmed down to partial factorials and hoping to minimize the amount of test steps that have to be done and still yielding the same effect. So if the hardest part of setting up a DOE is selecting the correct factors and levels, and we have discoveries in HALT that assist with the selection of these factors, a DOE is a very big investment in time and resource. Now, a DOE is entirely based on what was selected to adjust and monitor. So Doesn't it seem like it would be of tremendous benefit to have experienced some relationships between stresses and failure modes? And you can do this very quickly in HALT testing within just 2 or 3 days. You can begin to see these relationships, and that will help shape the factors that you select. So in doing this, you'll see a direct link of inputs and outputs to the experiment. And, you can do lots of different manipulations with the results in the DOE. You can do response surface analysis, and you can begin to see if these relationships are consistent. So you will get confirmation that you selected the right factors and help reduce the number of iterations you would have to do for a DOE traditionally. Fault tree analysis. So a fault tree analysis is a deductive approach for resolving an undesired event and its causes. So you're starting this, unlike the FMEA where you're speculating about failure modes, you have an identified failure mode that you want to understand better. And a lot of times, FTAs are represented in logic diagrams similar to this. So if the objective of HALT primarily is to expose failure modes, it's quite clear to see how this would work very well in conjunction with an FTA. So in a traditional HALT, you would expose a failure mode through high stress and begin that process of trying to understand what happened. Well, why not do it in conjunction with the formal FTA process, which includes the whole team and a much broader spectrum of information doing that analysis? So in this example here, we are able to, with components that were broken free in the HALT testing and realizing they were sensitive, we're able to then look at what are the factors that drove that issue, which ultimately resulted in a lost signal. And then there's looking at it going in the other direction with the fault tree analysis, helping drive where to look in HALT testing. Let the HALT testing help you with doing a fault tree analysis. So in this case, with the fault tree analysis, coming down to try and figure out what the factors were in this logic diagram, not being able to clearly speculate what would happen in combination with vibration that would lead to the lost signal. So taking that and using that as input to design the HALT test, you're going to focus very much on this signal consistency as a metric and what metrology you should have around the components that drive that signal. And when you observe these components that were able to break free very easily, you now have an understanding of what some of the factors are. So this fault tree analysis will not only be done quicker, but it'll be completed with much more confidence of having made the right associations. Wear out. So if we're going to use wear out as a metric, what do we want to improve with wear out? We want to extend useful life. Now, like I said before, there's lots of ways to do this. You can use preventive maintenance. You can recommend replacement of entire product or change of application. But of course, this requires intervention. So what would be great is if the design itself had a wear out phase that was much farther out. So what tools in conjunction with HALT can we use to do this? So accelerated life testing are tests that are specifically designed to be done where the product is exercised, but within a shorter period than the normal wear out period, a life statement can be made. And this is typically done by using established acceleration models. One is the Kaufman-Manson model. One is an Arrhenius model. There's also a Power-Weibel model. And these are probably some of the most common ones used. So for the Kaufman-Manson model, it uses increased temperature range cycling to demonstrate useful life. So I've used this model commonly when I have a product that I believe its primary wear-out failure mode is driven by temperature change. So we're looking at a product that breaks down because of thermal expansion and contraction. And this can turn into a very high physical stress if you have dissimilar materials that are in contact with each other, or a large mass that's going to have a big temperature gradient from outside to inside as you go through a rapid thermal transition. So with the Kaufman-Manson model, you can expand those temperature ranges and effectively accelerate the wear out and then make a statement on the regular wear out. Well, this is a lot like the rapid thermal transition stress of HALT, where in HALT you have a phase where you're doing temperature transitions as fast as possible to create these physical stresses as fast as possible. Now, it's very difficult and not common, and I don't recommend trying to make a life statement based on the failure responses in HALT from this rapid thermal transition. But what have you learned? You've learned what these primary wear-out failure modes are most likely going to be. And you've gotten a feeling for the temperature ranges that create absolute destruction. Well, this is very valuable information when setting up an accelerated life test, because you don't want the accelerated life test temperature ranges to go into that destruct range. Because if you're creating destruction by going to such far extremes that you're no longer modeling the wear out, you now have a data set that's effectively contaminated or could actually be dangerous if you try to make a life statement on it. You've also learned what you want to measure for a response. What are those wear out failure modes that you think will be driving the useful life? And you've had a chance to see those in the HALT test, even though you may not be able to make a correlation statement. But what you have done is set up an understanding of the relationship for the accelerated life test. How about the Arrhenius model? So with the Arrhenius model, what you are looking for is material breakdown based on thermal stress. So I've used this model a lot when I have a product that operates at effectively a set temperature. It doesn't vary a lot. And the primary wear out failure modes have to do with material breakdown from this thermal stress. Well, with the Arrhenius model, you can set up a calculation where you can run the product at a higher temperature level and then make a predictive life statement based on those results. Well, again, the same with the previous rapid thermal expansion with a hot step stress. You're operating the product at a consistent temperature in stepped increments, and you're looking for the failure mode in HALT testing. Now, again, it's very difficult to make a life statement on that, but you've learned things that can help you set up a better Arrhenius-based accelerated life test. You will know what are the temperatures that cause absolute failure. And knowing these ratios between that and the normal operating temperature can help you select the right temperature that you are confident you're not creating failure modes or destruct levels that would not commonly occur in the field. So you can see how doing HALT in conjunction with these greatly benefits these accelerated life models. How about HALT and root cause analysis? So HALT yields a high number of failure types in a very short period of time. This offers the opportunity to begin to investigate and classify failure types early. So when you're doing something like a root cause analysis for any type of test, the most important distinction is this a wear out failure mode or a stress failure mode? One of the most critical programs, I believe, is a reliability growth program, where if you are not able to clearly distinguish between a stress-related failure mode and a wear-out failure mode, your results can become very contaminated. So if we look at this chart, let's say from a regular usage cycling for a reliability growth program, and you're plotting usage time to failure rate, you're going to see the product start out as a prototype at a very high failure rate that's slowly going to come down as you make improvements. And you have a goal, which is that blue line that you want to reach. So at some point, you're going to reach that goal as you continue to improve the product. And your hope is that effectively the failure rate stays static at that point. So that flat green line is effectively representing the bottom of the bathtub curve, and you've demonstrated your goal, your advertised reliability. But as we know, at some point, the wear-out failures are going to become dominant. And they're going to be based around some average time of wear-out. So if we were to only look at wear-out failure modes, we would see basically a failure rate of effectively 0, because wear-outs are not going to occur early. And at some point, these dominant wear-out failure modes are going to begin to become present, and the amount of population they affect will continue to increase. And you could make a statement on wear-out failures. But what happens if you can't distinguish clearly between the two? Well, if you can't, what's going to happen is you will be able to calculate, based on your stress-related failures, the bottom of the bathtub curve, your demonstrated failure rate. But as wear-out failure modes begin to occur and you cannot distinguish them as different than stress-related failures, all of a sudden that failure rate you're reporting is going to begin to increase. And you're going to be reporting a poorer failure rate than your product actually demonstrates. And it's going to look like you're having issues that are driving the inability to support your reliability statement. So you've effectively begun to report on the last phase of the bathtub curve, when what you really want to be doing is making a statement on the bottom half. And any wear-out failures that occur in the reliability growth program should be removed from the calculation. But again, if you can't distinguish between a wear-out failure mode and a stress-related failure mode, you can't do that. Used in conjunction with HALT testing will have given you this great opportunity to observe stress relationships to failure modes. And it will be very helpful in defining your root cause analysis techniques that would allow you to, with confidence in your reliability growth program, distinguish between these two and ensure what's on this graph doesn't happen. And you're only reporting the true failure rate during useful life. What about HALT and stress strength analysis? So stress strength analysis is the probability of failure based on the probability of stress exceeding strength. So in a study of wear out, SSA can derive a correlation between an increase in usage stress and shortening of reliability or useful life. So this can lead to wear out being part of the reliability being defined at multiple levels based on usage conditions. So this will assist with making statements or commitments to your customer under different usage cases. So a lot of times with a product, you might advertise different reliabilities for different usage cases. A low stress usage, you might say you will have a 99.99% reliability over 10 years. But as you can see here, it incrementally goes up. And under an abuse case, you could say, well, you're only going to have that reliability over 2 years because under those high stress conditions, the population will not yield the same reliability. And this can be okay, only as long as it's constantly communicated to the customer and they understand that under the case they're using, which reliability you're committing to as a supplier. So used in conjunction with HALT, HALT will identify these stresses which drive these failure modes. So by identifying these in advance, the stress strength analysis test can be executed with much more focus, can be much better designed. So you can see the theme here in using HALT with a lot of these other tools. What happens is you're able to, in advance, understand the fundamental relationships between stress and failure mode. So time will be saved because the correlation between these is understood in advance. And all these other tools yield much greater results because in designing these other tests or doing these techniques, you've gone into it understanding the product better. So if the bathtub curve is our metric, we want to shorten the infant mortality. We want to lower the failure rate during useful life. We want to push the wear out as far as we can without having intervention in the product. And if we do that, this could be our new bathtub curve after HALT. Because HALT used in conjunction with these other tools, you now have a product that has much better yield in manufacturing, much lower warranty cost, a failure rate that can be better than your competitors, and that you can confidently state is better during useful life, and have a wear out that's further out, a product that lasts longer. Thank you very much for attending this. I'm very happy to continue this discussion or even do a lunch and learn with your team. If you'd like to contact me through email, you can, of course, go to my website at any time and contact me through there. And I wish you great luck in all your work with HALT testing.
I'd like to thank Adam for taking the time out of his busy schedule to present today and remind everyone that his expertise extends across multiple industries, and he's a great resource for any organization. So if you'd like to speak directly with Adam, he can be reached at abarrett@apexridge.com, or just send Qualmark an email at marketing@qualmark.com, and I will directly put you in touch. Thank you very much, everyone, for attending today's Qualmark Ask the Experts presentation. And I encourage you to please visit our events page on our website to keep abreast of all of our upcoming free webinars, and browse the resource page that has a wealth of archived webinars, white papers, articles, and a bevy of other helpful tools. So thank you very much, Adam, and thank you everyone who has attended today. We look forward to having you on a future webinar. Thank you.